Max Ortiz, United States, and Sweden. Mexico.
Yeah, there was some problem
Some
there.
errors here. Mexico. Please.
Thank you. Can you hear me well? Yeah. In this talk, I'm going to present some of the work we have done in robotic prosthesis. Here, you can see how patients treated with osseointegration I fitted with my electric prosthesis. These patients, as any other amputee, can use two types of prosthetics. In this case, I'm showing hands. Simple 1 degree of freedom hands that can open and close, or more sophisticated prostheses that can do more things, that have individual articulated degrees of freedom. This means in this case that the fingers can move independently. However, they are controlled in pretty much the same way from the patient point of view. In this one here, the patient is missing some fingers, and in this one here, he cannot control all the fingers. So the control is not very intuitive in most of the cases, and he cannot profit of this nice hardware. So if we look at the state of art of prosthetics today, we see that we have a nice hardware, these hands, but we don't have enough information to control them. So what can we do to improve that area? So we can look at where do we get the signals from and how we do it. And once we have the signals, how we break them down with filters we use. We use pattern recognition to know what the patient want to do. And once we know what the patient want to know, which control technique we use to tell the hand what to do. So we work in all of them, basically. We start with the biopotential amplifiers. We're in the 3rd generation right now with this one here. They are compact, low power consumption. They are designed to amplify signals as small as 1 microvolt. That's very small signals. I don't know how many engineers are here, but you get in a lot of troubles when you try to do that. They have properties that are better than standard amplifiers you can buy commercially. And then we design a pattern recognition system as well. And we try to change some things to improve our chances to have a better success. But we did the same than other research groups was to use surface electrodes, so 4 channels. We put them just equally distributed, not putting them in any specific place on the muscles. Then artificial neural networks as the pattern recognition algorithm, single-layer perceptron and multi-layer perceptron as the topologies. And then we tried to look at which filters we were feeding these neural networks with. And there's not so much work done in that area, but we tried to optimize a set of filters looking at 21 in time and frequency domain, some of them just statistically, some statistical descriptors, some of them more physical properties. And we use a genetic algorithm to optimize in accuracy, convergence, and speed. We also try to biologically inspired algorithms for the training of the artificial neural networks. That's particle swarm optimization and evolutionary algorithms with backpropagation algorithms for benchmarking of the other 2. And finally, we have a system that's able to recognize 10 patterns with accuracies over 25%. These are the patterns over here. And we have a set of filters that allow us to use them with a better convergence in more patients, this 10%. With convergence, I mean sometimes the signals are not strong enough and that will cause problems in the pattern recognition. But with the set we have, it's, we could test more subjects. There's going to be a paper published about this soon. So you might think that we have these nice robotic hands, and we have a system that can do 10 patterns, or probably more. We tried 10 because like, we can even control these 10 already. So why don't we feed patients already with this system and those hands? Well, the problem is the stability of the signals. You have a lot of practical problems when you do surface recording. For that reason, we look at implantable electrodes. There are several studies that shows that long-term, in the long term, the signals are more stable when you are inside of the body. So we look at all kinds of electrodes. Here I'm going to present neural interfaces, as the name of the talk said. This is a sieve electrode. And the way it's implanted is by severing the nerve, and then you take both ends inside the conduit here, and they will grow through these holes where the electrodes are. The advantage of this electrode is that you get information from everywhere in the nerve. The problem is very traumatic implantation. It only been tested in animals, as far as I know from the literature. And a little bit less invasive electrode is an array of needles that are very small in different lengths. This will allow you to get information from different groups of axons. This has been used in acute experiments in humans, and the subject report no loss of sensibility of movement. But again, it's still quite invasive. This electrode is more common, is inline intravascular electrode. This is an example. So you'll have the electrode here that's like putting a suture on the nerve with the contacts inside a fascicle, and this green area will be the recording stimulation field. It's less invasive, but you have less information from the nerve. A solution to that is a transverse design that will go in this direction instead of longitudinal. It's been used chronically in humans, but it's not as common as the cuff electrode. This electrode have several different designs. It can be a self-sizing spiral cuff or a rigid cuff. Shape memory alloy has been used in this electrode as well. You can have ring contacts or discrete contacts, not that common. And it's been used in patients for stimulate the optical nerve in blind patients, stimulation the vagus nerve for preventing epileptic attacks. Foot drop correction, pain control. One group used it to read signals from the skin to control an automatic system for grasping. So the patient will feel, if he's holding a cup and the cup is sliding, then feel that with the skin and increase the stimulation in the muscle so he can grasp it harder. The problem when you do recordings in the nerves is the signals are very small, in the order of microvolts. And then you have muscles around them. And the amplitude of those signals is in the order of millivolts, so it's very easy to mask these small signals. The cuff isolates some of that noise, but there is always noise coming in on the sides. And therefore, you have different configurations on the contacts. It will be a bipolar configuration, a differential measurement with two poles, a tripolar where you do a short circuit between two ends, and a differential measurement with the center. And then you can add two other rings and do another short circuit here that will reduce the noise. The idea is that here you take the average of the noise that is introduced in the cuff, and when you subtract that from the middle, that will theoretically give you zero. Not always, but it works very well. It's less invasive, and the only problem is that the recording field that you have is mostly of the axons that are in the periphery of the nerve. So we try to optimize this electrode for getting more information and do pattern recognition with it. If you have ring electrodes, this will be your recording field, if this is the nerve, because you are doing the average of the action potential that's going on in this part. But then you can split the rings and have discrete contacts and do a tripolar measurement in different size of the nerve, which give you theoretically a little bit more of information. The problem is that when you split the rings, you might destroy the ability of the triple to work. Therefore, we did an experiment with Professor Jan Delbecq and Jorge Marin at Université Technologie Louvain, where we tried three different rings, and we tried three different electrode designs, a full ring, discrete, and semi-discrete, where we investigate how the triple will work, how the short circuit triple will work, the bipolar configuration, what happens if we increase the area, if we move the contacts away from the ends. What we did is we used the sciatic nerve of a frog, that will be here, and a stimulation electrode, and then the recording electrode, one of those three designs, and repeat with the three of them. And then to simulate the noise from the muscles, we introduce a signal here on the same frequency that the muscles will peak, that will be around 200 hertz, with enough amplitude so we can record it and compare how we reject that noise from one configuration to other. This is how it looked like. So you have the nerve, stimulation electrode, the recording electrode. Just going to present a few of those results. Here on the left, you have the filter signal, and on the right, you have the noise. In this part here is the stimulation artifact. So we stimulate the nerve in this point. A couple of milliseconds later, you have the component action potential. And then we can measure the amplitude of the noise and the amplitude of the component action potential and the stimulation artifact. So what we want is to have this amplitude bigger than the noise so we can actually amplify that signal, because otherwise it will be masked. And we compare that. The blue is a bipolar against a semi-tripolar configuration. And here you can see the amplitude of the noise. It's dramatically, well, considerably decreased. And the same happened with a complete discrete tripolar configuration. So here is the signal-to-noise ratio against the stimulation artifact and the noise. In both cases, the tripolar, even in the discrete part, worked very well. Why the signal-to-noise ratio has to be bigger than 1? Because it's smaller than 1. That means the noise is bigger than your component action potential, and that means, yeah, exactly. That means that will saturate your amplifier, and you won't be able to get the signal you are interested in. So now you can think again. We have all these nerve electrodes. We can get a lot of information from. Some studies show they are stable. Why don't we use the system we have, these nice prosthetics hands, and the electrodes to fit patients with them? Well, the problem is how to get those signals out of the body. And that's been a problem since the invention of implantable devices. How do we communicate to the implantable electrodes? And it's there where the osseointegration comes in. We have developed a long-term stable human-machine gateway, call it like that by now. And the idea is that we can have any implantable device communicate to outside the body. So we can have a mix of electrodes inside and then a sophisticated robotic prosthesis in the outside. This will open a lot of possibilities for developments in more complex hands, like the Smart Hand, the project going on in Europe, or the DECA arm in the States, or the Johns Hopkins University. This is a piece of an article that came out this month in Dagens Medicin, a Swedish newspaper. The system is a little bit more complicated than what you can see there. We have a prototype manufactured already, and we're looking forward for the first clinical trials. And you're probably going to hear more about this later on. So we're very excited about this, because we think is the key part for a long-term implementation of more sophisticated steering of prosthesis. So our first intention will be to take these prostheses that are already available in the market, use the pattern recognition systems that are available, muscle electrodes or a combination with nerve electrodes, and provide more movements to the patients what they can have right now. This project is running in collaboration with Gothenburg University, Richard Bronemark and Björn Rodevik from the Department of Orthopedics, Peter Thompson in the Department of Biomaterials, Steve Johnson, Sahlgrenska University, Chalmers University of Technology with Bo Håkansson from the Biomedical Engineering Division, and Integrum AB. That's my email, and you can write me if you have any questions, or don't believe something what I presented today. Thank you.
Thank you very much, Max. This paper is now open for discussion. We have time for 1 or 2 questions, please.
So Max, that's a lot of fascinating work, and obviously we can talk all day. I'll ask one question for this audience, though. As you look at doing peripheral nerve recordings from a cuff and are planning to use pattern recognition, have you got any data that anybody's been able to do pattern recognition off of a nerve cuff recording with any fidelity?
That's a very good question. Actually, people haven't used much these electrodes for pattern recognition, and I'm guessing because they couldn't have a good access to them. There is a group in Italy that use intravascular electrodes for pattern recognition. Maybe you hear the Life Hand project. It was 30 days implantation. There's nothing published yet, but I was in a conference a couple of weeks ago in Aalborg. They work a lot with different electrodes, and I hear people is doing some pattern recognition now with cuff electrodes. So we'll see who can publish first.
Well, good luck.
Max, that was fascinating. I'm Jonathan Forsberg from New York City. I'm encouraged that you're using artificial neural networks for your pattern recognition, but one question I had was how long do you think it will take to train each model, and will it need to be retrained periodically? Because training of these models is labor intensive, both from a mathematical and engineering standpoint.
Yeah, well, the training takes a couple of minutes. That was one of the things we wanted to optimize with this all different set of features. And one of the reasons why it's hard to implement this technology with surface electrode is because of the retraining part. So after a while, the surface electrode will move around the muscles where the signal you were picking up originally, or the patient will sweat, that will change the impedance, which will change the signal. So the pattern recognition will work for 2 hours, but then later on, the signal will change that much that you will need to do a retraining. Is that what you? So that's a problem to have the retraining in a microcontroller. It's kind of hard. If you do it in a PC, it goes.
So I think that's why it's important to have a feedback loop, and unfortunately, neural networks are not well suited for a feedback loop. So there are some other methods, some probabilistic methods, like Bayesian belief networks, for instance, that do much better with feedback loops. So you may consider that.
Yeah. Well, this was one of several algorithms that's been used for training these kind of problems. So we're consider some others at the time.
Thanks, Max.